Welcome to a new lesson. In this lesson, we'll be discussing properties of linear relations. Let's take a look at the table below and the graph next to it. The table values and graph show the cost of pizza with up to 5 extra toppings. So let's discuss number of toppings for pizza. Initially, we started with 0 toppings, and the cost of that pizza is $12. For each an additional topping, we have an increase of 75 cents. This means that from $12 we jump to $12.75, then an additional topping will cost 75 cents more to $13.50, and again for each topping there is a 75 cents increase. Also notice that since we are increasing by 1 topping, from 1 to 2, from 2 to 3, from 3 to 4 by 1 topping, from 4 to 5 by 1 topping. It's progressively increased of 1 topping and a progressive increase per each topping for 0.75. As long as these increases are the same, the graph will be a linear relation. What does this mean? That a graph, if we plot the number of extra toppings on the x-axis, the independent variable, independent, while the price is dependent, it will make a straight line. This means that for each topping, we have an increase of 75 cents. This means for increase of 1 topping, we have always constantly the same increase of 75 cents. This makes a linear relation. Let's use this information to answer a couple examples. In this table of values, it represents a linear relation. Justify the answer. Well, actually, which table of values represents the linear relations? And justify the answer. So the first table is a relation between temperature in degrees Celsius and a temperature in degrees Fahrenheit. So let's take a look at the changes. From Celsius, we're jumping by 5 degrees. From Fahrenheit, we're moving. So how do we find the difference? 41 minus 32 is 9. And then the difference between 50 is 41 is 9. And again, between 50 and 59 is 9. And between 59 and 68 it's 9 degrees of Fahrenheit. Because we're consistently moving with Celsius by 5 and with Fahrenheit by 9, this indeed is linear. The relation between the current I and the power P in an electric circuit is described in the second table. So let's take a look at what's happening. We're increasing the amperage by 5 amps each interval. And as long as we have the same power increase, not necessarily 5, but a constant power increase, then it will be a linear function. So from 0 to 75 is 75. From 75 to 300 is 225. From 300 to 675 is 375. And then from 675 to 1,200 is 525 increase. Notice these increases are not the same. They need to be the same for a linear function to occur, or linear in this case relation. So this is not linear. Let's continue with another example. In this case, we're going to determine whether an equation represents a linear relation. And this time, instead of having a table of values and a graph or a table of values, we just have an equation. We need to graph these equations to see if there is a relationship for a linear relation. So how do we graph these? How do we graph the first equation? y is equal to negative 3x plus 25. The way we graph it is by drawing a number line, not a number line, but a table of values. So the first thing we'll set up is x and y table, and we pick arbitrary values of x. Usually we start with a negative 2, and we go with negative 1, 0, 1, and 2. Then how do we know the values of y for this case? Well, we plug these values into our equation. So y is equal to negative 3 times negative 2. That's the first x value that we arbitrarily picked. And of course, don't forget 25. When we do these calculations, we'll find that the value is 31. So this is 31. We continue on, and we use the second value we chose for x, which is negative 1. And then, of course, we plug it back to the equation. In this case, we get the value of 28 for the y. Then we continue in, we'll plug in 0 for the x. So negative 3 times 0 plus 25. In this case, we get 25. Usually, it's a good practice to have more than 3 coordinate points for x and y values. In this case, we have 5. So we plug in this time a 1 for the x into the y equation. That's 25. And that will equal 22. And now, what about for the last x value, which is 2? We plug that in. And now we get the value of 19. So with this table of values, we have 5 coordinate points, which we should draw on a graph. So let's find these coordinate points. The first coordinate point is negative 2 and 31. So our x value is negative 2, and we go up to 31, which is approximately right here. The next coordinate point is negative 1 and 28. So negative 1 is here, 28 is approximately right there. And moving on, 0 and 25, and 0 and 25 is somewhere between, it's right there. And 1 and 22, 1 and 22, and 2 and 19, and 2 and 19 is somewhere right here. So notice that they do, if you draw a straight line through it, they're pretty much on the same straight line. So make sure those dots are present. They're pretty much on the same straight line. You could also double check if this represents a linear relation by saying to yourself, okay, well, what's the difference between these two? The x values. Well, they go by the increments of 1. And the y values, they go down by increments of, in this case, 3, consistently. Since both of the increments are consistent, they're not changing, therefore it is a linear function. Let's now do, with the same procedure, the next problem right here. So in the next problem is let's identify if y equals 2x squared plus 5 is a linear relation. So we're going to do the same procedures before. We're going to have x and y value, and again, pick arbitrarily negative 2, negative 1, 0, 1, and 2. As long as it's consistent for you, that means the x values increase or decrease in regular intervals, let's say in this case by 1. It doesn't really matter which x values you choose. It's usually better to choose small values like 1, 2, and 0. So again, we're going to take these values and plug it into the x values into our equation. So we have 2 times negative 2 squared plus 5. Make sure you put brackets when you do your calculations. In this case, when x is negative 2, we get a value of 13. So we have our first coordinate point. Now again, plug into our equation negative 1 for x. into our equation, and then we get 7 for our answer. That's our second coordinate point. Now again, we'll plug in a 0 for our x value. Don't forget to square. In this case, it wouldn't really matter. It still turns into a 5 because 0 squared is still 0, and 0 times 2 is 0, and 0 plus 5 is 5. And then the second last one, now we plug in 1 for x, and the answer then is 7. And the last one, we plug in 2 for our x value, and the answer turns out to be 13. Now we need to graph it. So in this case, we're doing a rough sketch. So we're going to graph -2, so we start from the left-hand side, and 13. So -2 and 13, well, we know that this way is about 10. So 13 is a little bit above 10, but below 15. Half point between 10 and 15. So it's somewhere right here. That's the coordinate point for -2 and 13. What about for -1 and 7? -1 and 7 is about here. So that's done. And what about 0 and 5? 0 and 5 is about here. 1 and 7. 1 and 7 is about here. And 2 and 13. 2 and 13 is about like this. So it actually will turn out to be like this. If we do it a little more points, it will look like a curve. So it is clear for us that it is not a linear relation just because it does not make a line. Not linear. It's a curve. Also, you could see that we are increasing by increment of 1 for the x, and if you look for the y, it's not consistent. We're decreasing by 4, then by 2, then increasing by 2, and then increasing by 4. It's not the same. And that's why it is not a second time linear relation. Let's move on to triple I. Again, with the same procedure, persistence is needed. -2, again, arbitrarily pick some y values. And in this case, we're trying to put in values of x, but there's no values of x to put into this equation. It's always going to be 5. So for any value of x, the y is always going to be 5. So how do we put this kind of graph on our, well, how do we just draw this graph? Well, if it's always going to be, if our y value is always going to be 5, and it doesn't matter which values of x we choose, so let's just put a 5 on all the values we chosen. So -2, -1, 1, and 2. And make a line in this case. Now this line goes forever left and right. Is this a linear relation? And the answer is yes. It is a linear relation. Because it makes a straight line. Also, if you look at the table, we notice that the x values increase by a factor by 1 always, and the y are not changed. That means they change by 0. Because of this fact, it's always constant, changing. Even though if it's 0, it's still a line. It is a linear relation. Now let's take a look at IV, or 4. X equals 1. So again, let's establish this table of values. And now x is always equal to 1. This means that for any value of x, so let's just pick one, like -1, 0, 1, and 2. the x value will never change. So let's, this is 1, this is 2, this is -1 for a while. Let's just graph this on your calculator, on your grid lines. So 2, 4, and 2, and -4. Now let's plot these. So where's 1 and -1? So 1 and -1 is here. 1 and 0 is right there. 1 and 1 is right there, and 1 and 2 is right there. And let's draw a straight line. Now this is a vertical line. It's still linear. And also if you look, the x values don't change. It's constant 0, changing. And the y values increased by 1. So it is constant in this case. And that's why it's a linear relation. Let's take a look at another example. We can identify a linear relation. So which relation is linear? Justify the answer. Instead of having graphs, equations, or table values, now we have more or less real life scenarios. A new car is purchased for $24,000. Every year, the value of the car decreases by 15% from the original. The value is related to time. Is this a linear relation? In this case, let's set up a table of values to see that indeed or not, that the value changes with time constantly to be a linear relation. So I'm going to have time, and we're going to have value. So when we buy at time 0, the value is $24,000. Now, what happens as the first year? After the first year, the original value decreases by 15%. Therefore, it is at 85%. So what is 85% times 85 over 100 of 24,000? And the answer is 20,400. Now for the second year, the value is now 2400, and now it decreases by 15%, so that means the second year will have 85% of that value, which is 17,340. For the third year, we have a new value, and that decreases by 15%, so we have 85% of the original of the value from the second year, and that value is 14,739. So if this was a linear function, time is decreasing by 1 year or increasing by a year, and this, the values of the car, have to also be decreasing by the same amount. But if you notice, if you subtract one from the other, you notice the differences are a little bit, they're not the same. So the difference between, the drop in price between when you buy the car in the first year is 3,600. But the drop between the years of 1 and 2 is not 3,600, but 3,060. And then from second to third year, if you subtract 17,340 and 14,739, you get a drop of 2,601. So notice that this is called depreciation. The cost of a car decreases as time goes on. These values are not the same. Therefore, this is not linear. It's just not linear. Let's take a look at part B. For a service call, an electrician charges $75 flat rate plus $50 for each hour he or she works. The total cost for the service is related to time. So let's set up a similar table when we have time and when we have a cost. So at time 0, it's the electrician charges $75. Then for the additional hour, there has to be a $50 charge for each hour, so it's now $125. For the second hour, we add in one more 50 for each hour, which is $175. For third hour, we add another 50, and that turns out to be $225. Now, should be clear that the difference in price between 75 and 125, 125, 175, and 175, 225 is 50. That means the cost is increasing constantly, while the time also is increasing by 1 hour or by constant time rate change. This means that this is a linear relation. Let's take a look at one example. Now we have a graph. A water tank on a farm near Swift Current, Saskatchewan holds 6,000 liters. Graph A represents the tank being filled at a constant rate, and graph B represents the tank being emptied at a constant rate. Identify the independent and dependent variable, and then we're going to determine the rate of change for each relation. When described, what does it represent? So let's first talk about the independent and dependent variable. Usually the independent variable are located on the horizontal axis. And in this case, the independent variable is time, while the vertical axis is the dependent variable. Is dependent. And that dependent variable is volume. So what about the rate of change? Now the rate of change is what's called rate of change. There's a specific formula for this. It's considered rise over run. Or in this case, it's also considered slope. And what is this rise over run? Well, the rise over run is in other words division, or a ratio between, in this case, the dependent variable, and the independent variable. So let's take a look at it. I'm going to draw you the run and the rise. In this case, our volume is 6,000. So for 6,000, it took 120 minutes to fill. And the rate is 6,000 over 120. So 6,000 over 120. So that's liters over minutes, which equals 50 liters per 1 minute. So this rate tells you how fast we're filling up this water tank. That means in 1 minute, this water tank was filled with 50 liters. So that's for graph A. For graph B, on the other hand, let's erase the independent variable. For graph B, we started with 6,000 I'll use the same color, 6,000 right there. So that is our rise, that's our rise, 6,000. And the run is 60 minutes. And don't forget that 6,000 liters that we're trying to flush out or empty. And if we do the operation, 6,000 divided by 60 is 100 liters per 1 minute. This means that we emptied the entire water tank at 100 liters per minute. So that means every minute, 100 liters was emptied out of the tank. Mathematically, there is a little bit of a difference between these values. Not just because one's 50, one's 100, but because since we are emptied this tank, we give a specific operation to it as negative. And how do we know that one graph represents a negative or a positive rate? Because the graph is moving up and towards the right for graph A, we consider this as a positive rate. But since the graph, as we move right, moves down, that is considered as a negative slope. And that's why the emptying effect of this graph has a negative rate. And that's why it's important that we put the negative 100 liters per 1 minute as the emptying effect, as a negative rate of change. This concludes our lesson.